Okay, let's go to talk about collaborative AI methods in robot navigation. And that is a topic that is now very important because in the future, robots and humans are going to work together in many of the daily tasks, and not only in the industry or in the companies, but also in our life. Probably we will have robots at home. We will have robots in the cities, in the buildings, and we'll do tasks together. Okay, you can see here one example of what happened when there are many people across, and you think now humans. In the future, you would see humans and robots doing this kind of events. People are working together, people are, in this case, are navigating together, but there are many interactions that can happen now only in motion, but also in other types of interactions. Okay, we expect to see social robots helping people to do their daily tasks, and you see some of the tasks, help elderly, carrying baggage, going shopping, transporting products, or shopping. What are the interaction topics? Okay, one part of the interaction topics is in human-robot interaction is coexistence or cooperation, and you can see this. But another is collaboration. Collaboration is when robots and humans share the same goal and role and try to do their best to achieve that goal. Okay, now we will, in this talk, I will talk of different topics, not all, so only some of them, that we are doing in our institute. We do accompany people, we are our robot approach people, also engage people in order to start an interaction. Also, we have been working in search and follow people. Another is collaborative search in human and robot. And the final one, I will talk about handover operation. And let's going to go a little deep in each one of these. But before, let's go and take a look at what are the elements that are required to be able to do this collaborative human and robots. And you can see here that in the middle, there is the decision making, the process to make the decision to do the task together. And here we have the action of the robot, what the action will do. But in order that the robot can do, it has to perceive what is the environment, has to perceive what is the object that are around, what are the objects that are moving, what is the person to interact, what is the face of the person in order to identify, etc. Also, it has to do interaction, for example, social interaction. Also, it has to communicate. Human and robots has to communicate in different ways. And always they have to learn and adapt to the human, not only the human that they are doing the collaborative task, but also to the other people that can move around. Okay, let's go in a little more in deep. Perception, what the robot has to do, perceive, recognize the environment, identify and track people, and interpret the situation. This is the typical things that the robot is going to do in order to do a collaborative. But also, it can do a cooperative perception. In this case, for example, the robot has their own sensors, but can share their own sensor with the sensors of other robots. For example, this is a robot, there is another robot, and they share this vision. But also, there is environment perception from cameras that are in the building. There is our computer science faculty. But they also can share information from here, and with all this information, the robot will be able, this robot will be able to do the task. Okay, but what else? Communication. The robot has to communicate with the people through their dialogue, in speech, text, or visual, or non-verbal dialogue. That is a very typical issue that happens in between humans. When there is the relation between speech and human motion of the body, it is around, when there are few speech, it is 40% of speech and 60% of human motion. That is what is required to do communication. But sometimes it's much more of human body communication than the dialogue that we can have. But also there is implicit communication. For example, this human and this robot, or through a sensor, they are communicating each other. There are different types of the communication. Decision making. Decision making is usually what we think is part of the intelligence, no? Reasoning, planning the motion of the robot, reasoning about the object that we have, or the reasoning about what we have to speak or talk, etc. Also, there is another issue very important in collaborative, is intentionality. The robot has to know what is the intention of the human in order to help in doing the task. And for example, this is a giver, this is a receiver, and the giver has to see where is the human arm, is the motion of the human arm in order to approach this object to him. And also there is an agreement. When we do collaborative actions, both the human and the robot has to agree with the plan. And if not, that will be not able to do the collaborative planning. Okay, interaction. Usually, typical interaction is the social interaction with the rules of the society, of the cultural rules. But also there is physical interaction. For example, you can see here, physical interaction between the robot and human that do a task together. In this case, fixing one part, and the human is doing a hole in that. Or in general, there are many other types of human-robot interactions. That is typical ones. Okay, let's go into explain our example of collaborative AI, and I will explain that with these two robots and another robot. This is the TV robot and Davo robot, and another one that is the Ivo robot that you would see next. But also, you can see here the experimental settings where we do our experiments, and that is the Barcelona Robot Lab. Remember that you can apply in the Terrinet project for a project if you want to do research in our installation, and you will do in this installation. It is a Campus North installation of Barcelona Robot Lab that is 10,000 square meters. Here is the computer science faculty, and here are this is the students' classrooms, and there are departments. And here we do many of our experiments we do in this place. You can see some of the pictures in the UPC North Campus, and also this is in the South Campus. Then we do our experiment also, and there are different locations where you can do this kind of experiments. Okay, what are the robot sensors? In the case of TV and Davo, our sensor are GPS, a stereo camera, tactile screen, Microsoft speakers. There is vertical leader, horizontal leader. That was the ancient. Now we have a new ones that are 3D leaders, and then we don't use that one. We use here to 3D leaders. But also we have a new robot that is the Ivo that has also a mobile platform for outdoor environments, but it has 2 arms. And then they have also additional sensor, that is a force and torque sensor here in the wrist. Okay, let's go to start with an easy to understand collaborative interaction, that is in this case collaborative search. Our goal is a human and a robot has to look for an object that is in an outdoor place like this one. Like this is the North Campus, and there are some pieces of purchased pieces that has been put in the floor, and both the robot and the human has to do the exploration of this big area and try to do in a way that they don't repeat the same area, and they look different areas, and they share the knowledge in order to do this searching. And in this case, there is a collaboration between humans and robots. there is a computation of a multi-agent plan, that is a planner that not only plan what the human is going to do, but also plan what the robot is going to do. That is an important issue, because usually when we have a robot, we think the planning of itself, of the robot. But what is going to do the human? We don't know. Then in some way, we have to know the intentionality of the human, where the human wants to go, in order that the robot is able to do the planning of what the human is going to do. And then with that, he can do their own planning in order not to share the same area, and in this way avoiding to repeat areas that have been already searching. Okay. Then there is another issue. There is this human-robot communication, and then in our case, we created with a mobile phone. We created an interface where the human is able to see what the robot is proposed to do, and then with this, the human can change the intention of his own intention, where he wants to go, but also he can change where the robot has to go if he wants, and he can also replan that and do a replan. With this replan, in some way, it is doing the agreement between the human and the robot. If it does, the replan means the human doesn't agree what the robot suggests. If it doesn't do that, then it agrees, and the robot is going to do what the human and robot has agreed. Here you can see here a space with different rooms, and where the robot is looking and where the human is looking. And what you see here is the tree created by RRT, Rapid Exploring Trees, random trees, and it is what is done by when the robot plans the trajectory, its trajectory plus the trajectory of the human. Okay. Now here you see the human agent, you see the robot agent, and this is shared through this graphical interface. And in this graphical interface, you can see that the person can specify its position, although if the robot it is in an open area, can by its own sensor detect where the person is, but in case that is the person is in another room, then the person can specify its position, or is given directly by the mobile phone. Also, it can specify what is the robot goal. Also, can do where the intention of the person to go, and also can replan. And the robot can calculate robot position, robot path, and human expected path. This human expected path is done when the human specifies where it wants to go. Okay. Now you can see more in detail what is the architecture behind that. You have here the robot agent. You have here the human agent. Here is where the robot is doing many operations. The robot is, with the robot sensor, is perceiving the environment. Okay. Also with the robot sensor can track where the motion of the human, if the human it is in the field of view of the robot. And also the robot can have the robot goal in case that the human gives that, the human position, and in case that the person wants to replan. And inside of this, you have, this is a Monte Carlo tree search, that is a planning, a cooperative planning, that use the planning from the robot and the planning from the human. These both are done by the robot. I repeat, the human path planning is done using what is the own position, what is the intention of the person, and then the robot can compute one path that potentially the human can do. Okay, that is what is done every time. When this is done every few seconds, this process is done. that is updated continuously. That means then that is not doing once, that is doing many times. In order to be, why? Because the person can change their mind, its minds, and can modify its path. And then in this case, the robot will compute the new path every time, which it will replan its own plan. Okay. Now the process is through which a given team of agents explore a known space to locate an object. An object that is the space. The object can be, for example, in this position, and then the robot and the human has to explore all this space. Then the robot with the sensor detects this part, there is the covered space seen by the robot, there is the covered space seen by the person, and both are giving through this communication, and then the robot, for example, here is planning what it's going to do and what is going to do the human, okay? And then there is an observability graph, often a discrete representation of the search space is built, and there is an agent detection model, an object location probability, and a task modeling through one thing that we call source reward social, okay? And this is a decentralized variant of the Monte Carlo tree search, and when we want is to maximize a global team objective function, GX. GX is the global reward that we want to maximize, where there is the agent reward, there is the environment reward, there is the task reward, and there is the interaction reward. And you have here, and we want to maximize that, and we compute this maximization every time, then it has to do a replanning, okay? And this is done continuously. Continuously, every few seconds is done. It could be done in milliseconds. That depends on how fast is you process the robot, the computer of the robot can do every time. Okay, now you can see here an example of this multi-search. You have the architecture, and then you have the robot and the human. Then here is the robot and the human. Then they start to prepare the search, and then this is what is seen in the screen of the mobile phone. That is what the person can see. Where that is what is motion of the robot. That is the motion of the human, and then this is the person can see this every time, continuously can see in the mobile phone. Here is the space that has been already looked at, and that is the explored already area, and the violet is the part that has not been explored by the human or by the robot. And then finally, for example, this is the pieces. You can see there are very small pieces that are the one that has to be looked at. Okay, let's go in by another topic that is now let's going to do a company and approaching a task between the robot and the human. It's again a kind of cooperation between human and robots. And in order to do that, let's going to start with what we call human-aware navigation. The objective of human-aware navigation, it is that the robot has to do its own navigation in a way that doesn't bother the motion of the humans, the pedestrians that are around. Because if the robot is going to bother, then probably the people will not like to have robots in the streets, neither in the building, neither at home. Then that is why we call human-aware navigation, okay? Now, what is that? Okay, in order that the robot can do human-aware navigation, what it has to do, it is not only detect what are the objects around it, but also what is the motion of any object. Could be pedestrian, like this is the case, or could be a bicycle, or a scooter, or whatever that is moving around. Or could be a dog or a cat that is moving. It has to predict and predict the motion of them. And with this information, we will able to plan what is the trajectory that it has to do. Okay, that is the human prediction. And in here, although you cannot see because it looks like that is a flat view, but this you can see here is like a tornado where you see the bottom part is the time 0, and the upper part is the time 0 plus 5 seconds. And in some way, there is a tornado, then the robot perceives what is the motion of the whatever is moving around the robot, okay? And then with that, the robot will be able to generate a path in order to move in this area. Okay, now for doing that, what we have used is what is called social force model. That is work done by Kelvin in 1996, and what Kelvin was proposing, it is to have a model of the virtual forces than or in the mind of the person, but actually doesn't exist, but it's in the mind of the person, and the person uses these forces in order to be attracted by a goal where the person wants to go, and be repelled, or the repulsion, or there is a repulsion from the object that are static or in motion. For example, the person wants to move, the person usually doesn't move very, very close to a wall. They usually leave some space in order to move. Why? Because doesn't want to collide with the wall. And if something is moving in front, the person there is a big force that tries to move out from the trajectory of the person. And that is what I'm going to explain here. Okay, the first, that is the total force of the robot is going to do. And that includes the steering force. The steering force is what is the attraction of the force attraction that produce the motion of the robot. And that is, for example, it could be these two destinations, and finally the person decides to go in this path, and then with that we'll create a force. There is an attractive force that depends on the velocity of the robot and the desired velocities, and then with that, this attraction force then will attract this person to go to this destination. And then there are interaction forces. And these interaction forces are repulsive forces. And this, for example, the first force, it is the force produced by another people that are here that produce repulsive forces. Another is forced by static obstacles, and another is, for example, robots or whatever that could be. And in this case, all these forces, that is one way to compute these forces or repulsion. That is usually the decaying force. Then when you are very close, there is a lot of very high force. If you try to throw the wall, it is almost infinity force. But when you are far away, then the force is very low. Okay. Then this is what we compute every time. Okay, that is the force, and that is the force that will generate the acceleration of this robot to move to desired motion. Okay, you can see here what I explained before. The robot tries to move from one part to another. This is these tornadoes. Okay, that is actually the motion of the pedestrian or whatever, skaters or bicycle or whatever is around, then it's going to move. And what I said before, the bottom part is time 0, the top part is time plus 5 seconds or whatever, the time we want to consider. And that is the area of this tornado. This is the area when there could be collision in a specific time. It could be this collision at time 0, but then potentially much more collision at time in the future. Why? Because there is an uncertainty. This tornado increase because uncertainty what is going to be that motion, that object that is moving in the future. Okay. Okay. Now, for this, we created what we call anticipate kinodynamic planning. That is a planning that in our case was using RRT, then use the people intention and find what is the best path in this future, not in the present, but at the future, what is the best path to go. Okay, for that, we create an horizon where we compute this path, and this horizon usually it depends on the velocity of the robot itself. In this case, for example, it's 5 meters of horizon, when actually the robot will go farther away, okay? But that is our horizon. And you can see here the components of this planner. And you have the robotic platform, the planning, you have the horizon, this is the horizon, this is the destination where the robot has to go. And then it is the different path that are computed, and from this path, only one will be selected. That actually will be selected, this one, the projection is this one. But this is, remember that this is time in the future. Future 0, future plus 5 seconds or whatever here. And there are many, many different paths that can be done. Okay, let's go into see this in real experiments and what is the motion of this. This is the robot that is moving in our Barcelona Robot Lab in the campus node of the UPC. And you will see now different experiment where you can specifically see how is the behavior of the motion of the robot when the person is moving, and now look at the robot slow down and change the trajectory in order to avoid the person and be human aware, okay? You can see this in this part, and actually you see other people moving in front or by the lateral. Robot is always detecting all the humans around and track all the motion of the people and also it has their own destination where it wants to go. You can see here that it slow down and then increase the speed and then go into the place. Okay, we use this human-aware navigation in all our collaborative or cooperative tasks between the human and the robot, in order to be always human-aware and also avoid collisions and do it in the proper way, the human-robot task. Okay, you will see now, these people that were playing with a ball didn't take in account that this robot was moving. And take a look what happens here. They didn't perceive actually the robot is doing what it's doing, but the robot is doing, actually is detecting always the motion of the person and try to avoid them, although they don't have to be aware. Any of them has to be aware. Okay, let's go into use this human-aware navigation in a company of people. It's a company for one robot and one person, or one robot and several persons, okay? Now, the main objective, it is to obtain a natural robot-person accompanied method, okay? And avoiding static and moving obstacles in a dynamic urban environment. Take a look here. Here is the robot, here is the human that has to be accompanied. And for example, this is the destination, there is a static obstacle, there is to walk, and now the robot has to go, can go to this destination through this path, through this path, or through this path. The planner, the anticipative kinodynamic planner, will look which is the best path. Could be that this is the best path, or could be this is the shortest path. And take a look at the configuration. Here, the person and robot almost going in side by side, that is called accompanied side by side. But here, it has to change the configuration because both cannot pass at the same time. And then one, or the robot goes in front, or the human goes in front. And then it has to change the configuration and then to arrive to here. And then also here happens something similar, and that has to be taken into account always, okay? Now, for that, we have designed a special architecture that we call adaptive social planner. The adaptive social planner has as an input the estimation of where the robot has to go, okay? and also compute the social force model of the prediction of what is the motion of all the persons that are going to be, what are the repulsive forces that are going to appear. And also there is the localization of the robot itself, using there is a typically ROS localization and mapping. This is MECL, okay, the Monte Carlo one. Then we have here the adaptive social planner, then it does that. It computes every time multiple paths of all the people using the social force model, and this multiple path use a gradient descendant optimization and use an evaluation criteria in order to what? To select the best path every time. You remember that this is done every few seconds or every few milliseconds. That depends how fast you have the computer. And then in this way, there is the adaptive social motion that is done every time, okay? Okay, this planner has two parts. One computes, we plan all the paths using RRT, then propagate using the social force model. And the social force model has these forces. This is the total force, and has the attractive force, and that is the repulsive forces, okay? Now, and then when it's like that, that is multi-cost function, then evaluate different costs of the cost to reach the destination, the cost to avoid pedestrian, the cost to orientation to destination, the cost to control the robot, etc. There are different forces that are computed every time in order to look the optimal path that we will take it. For example, the optimal path could be this one, okay? The optimal path could be. Okay, now let's go to see one example with the accompanied one person. Here you have robot and person. You have this side-by-side accompany. Then typically what we want is the robot and human are has to be side-by-side. Otherwise, the robot could be in front or the human could be in front. In this case, the human is in front and the robot is back, but could be the reverse. And we have here the forces. Then there is the resultant force. There is the attractive force until the dynamic goal. There is the attractive force to maintain the formation. Take a look here. We have extended the social force model in order to be, this is attraction to the destination, but this is the attraction of the other person in order that the robot is close to the person. It doesn't try to go farther away, because if in that case, there will not be side-by-side accompany. And there is another force, and it is the repulsive forces, okay? And in this, if we take a look of the AI models that I talked before, there is part, we use perception to detect the accompaniment, to detect the person that the robot is accompanied, to detect the obstacles and track the people. We have communication between the human and robot. How? In this case, there is an implicit communication, because the robot senses where the person it is, and if the person goes further away, then the robot tries to approach this person, and that is the way to communicate. Also, there's a speech between the robot and the also, the robot can know the intentionality of the person, because it predicts what is the motion of the person, what is the person is going to do in the future. Also, there is an adaptation. The robot is always adapting its path, because always computing what is the prediction of the motion of the person and what is the goal that it has to go. And also there is an interaction through dialogue. The robot can speak and tell, don't go too far, don't go too fast, or close to me, or whatever. And also there is an agreement between both, because in this case, the robot use the distance of the person or the speech in order to know, to agree the plan to accompany the person, okay? And finally, there is the decision and reasoning of that. Okay, you can see here one example of one of the first experiments that we did with that. You will see that in this case, the behavior of the robot was not very good. Later on was improving a lot of, and you can see here these tornadoes, where is the motion of the persons, and you can see this person that is here, what is moving. Here there is the robot, and the person has to accompany, has to pass through this environment. And okay, what else? We did also this with UAVs, with a drone. In this case, instead of using a linear combination, we use deep learning, and in this case, a neural network, in order to compute the forces, the final force, and that was the combination of the forces from this is the forces from the obstacles, from the people, from the robots, whatever. And here finally we have the final force to move the robots. And also we have a human prediction, position prediction. There was another neural net, and with that we can do the motion. You can see here a graphical simulation with the robot and the UAV. Then is computed exactly the navigation between both. You can see here another of the motion of both, and you can see here the real one. Okay, the real one experiment with the flying robot, and there's the person, and the robots try to accompany the person and maintain the distance. Here there's an obstacle, and then both has to take in account this obstacle in order to maintain the distance and be able to accompany. The robot can accompany the person, okay? Okay, now let's go to see the same, but with two persons. In this case, there is two persons and one robot, and the robot has to maintain the formation with these two persons. And this is what is called V formation, where the robot is in the middle, is a little behind, and there are two persons on motion, and there are people that are moving around. And again, we use these forces, and you can see here, you can see here the force anti-group destination, and also the repulsive, and that is the force of the group to maintain the group, and that is the repulsive forces. And also we have the different elements that are considered, but in this case, there are two persons, no? There is the robot and two persons. And you can see here two different configurations of the robot. The robot is on one side, the two persons are here, or the robot is in the middle, and the two persons are out. And you can, in this case, it's a little more complex because the robot has to compute not only what the one person is going to do, but also what the two persons are going to do, and try to maintain this formation with the two persons. And then it has to compute where is the destination that it has to be reached. It has to compute the destination of one person, the destination of the other person, and the destination of the robot itself. And with all, it has to compute where it's going to be the final force. And taking account that here there are the destination of one person, the destination of the other person, and then what is the computation of each one of them, and then you can see the different elements, and then it's attractive, and also the repulsive forces with respect to people, and also the repulsive forces with respect to the environment. Okay, all of this has to be computed in order to finally decide which is going to be the path that is going to take the robot. Okay. Okay, we use some metrics to compute how good, how bad the robot is performing, and we use some area where the robot has to be together with the people in this kind of formation with the other type of formation. And with that, we compute the goodness of this approach. And you can see here one example of the V formation. Okay, it's going to see. You can see here, there is a typical, that is the UPC in the North Campus, where it's motion, and look at what happens. This guy is doing that, and then the robot, okay, it stops in one moment, but it continues. In the middle, there are other people. There is this robot is accompanying this person, but there is another people doing all of things. This is going to take a picture, but the robot has to continue and has to continue accompany that person. Here is in the V formation, the robot is maintaining the formation with these two persons, but it has to be taking account the motion of this person, the motion of this person in order to compute its own motion. You can see here the simulation, what is happening. Okay. Okay, what else? Approach. What happens when the robot has to approach to a specific person? In this case, it's a person is in a fixed position, And what we have decided in this case is that the robot, that is the person, and how to approach. You can approach directly front by front, or you can approach it in this position or in this position. That has to be computed by the robot every time. Every time means every few seconds or milliseconds, depends on how fast you do it. But also, you can do this approach when the robot is moving, when not only the robot is moving, but also the person is moving, okay? And in this case, we use this kind of social force model to compute the different forces. And you can see here, this approach, we'll see, okay, there is the robot is trying to locate in front of the person. Now you can see now that the approach is much better than before. Why? Because we have set up specific places where the robot has to be when it tries to approach a person. And you can see here the different path, and it's computed. In this case, there are two persons, and that is what is called a triangle approach. And in here you see the motion of the robot with people that is moving around, and the robot doesn't miss the destination, and finally it goes in front of the person to talk, okay? And here also some motions of the, again, trying, in this case, is motion of the person at the same time, and the robot move again also at the same time. Every time it's a little more complicated, and the robot has to finally reach what is the destination person and to approach to it, okay? Okay, again, there are all the elements are working together at the same time, in real time, in order that the robot can be able to decide what to go, okay? Now, another issue is engage people. Let's say what we have done now. To now is motion, no? Motion of the robot. Now the robot is trying to engage people to talk with them, okay? How we do that? Okay, what we did, it is first the robot has to look what is the person. For example, there is in our North Campus, in the Barcelona Roll Up, we have the robot, and there are people moving around. And then the robot is gonna detect that there is someone moving, and then tries to approach to it. Well, you know that typically happens when a person tries to, in the street, try to give you, to explain something, or try to attract to give some information. They do that, and we replicate that with the robot. Then the robot detects people, and then tries to approach it. And when it approaches, then start some non-verbal cues, is by the motion of the robot, and also verbal cues. It is talking and asking. And then if the person really stops, and then it can start an interaction. Then the engagement is created, because now the person is attending the robot, and the robot is able to make questions to the person, then the human answers. That is the human assistant process, and then finally the robot says goodbye to the person, because has explained whatever it is has been required. Okay. Now you can see here more in detail what is happening. There is part of in learning, because in this case in our detector we have an online learning face detector that detects the person and adapt to the situation of the person. And in this case, it's always using this learning in order to improve the knowledge about in this case, the identification of the person. We have the perception system that has the people detector by a leader, a target by the leader, and also by the stereo vision. We have also the human face detector using the stereo vision, and also the people detector we have here. And also we have the robot motion and actually capabilities, the plan trajectory to approach the person, express emotion. In this case, the robot has to illuminate the face in a way that expresses some kind of emotions. And then here there is the robot can ask questions to the person, and the person can give answers, and could appear some doubts. And the robot look for people, find a participant approach the people, create engagement, then do the experiment. Could be this the learning stage of the face, part of the face, give hello or bye-bye, and move around, okay? And the human, what it does, approach the robot, place itself in front of the robot, pick up away, control it in the case then use in order to answer question or whatever, and in here you have the part of the answer question. That is a typical experiment that we do in the engagement of people, robots and people. Now, let's go into another topic, and that will be one of the last ones, that is search and follow people. Okay, now in this case, we have this robot, and we have the odometry, and give us what is the position of the robot, also the laser, and give us the position of the robot, the cameras, that is the robot perception. We have an observation filter in order to look and follow a person, and that is the search and track of the person. And in this case, it's better to see directly. Okay, let's see. Okay, you can see here the two robots. There is not only one robot, there are two robots looking for a person that is hiding somewhere. And both has to look this person. And they share information. This is the person. The person is going with this tag. Okay. Now the robot has find the person and give information to the other in order that both can follow this person. Here you have the probability where is located the person, then are given and shared by both robots. That is the belief what is going to be, what is the person, and that is you can see the trajectories of one robot and another to look and follow that person. Okay, let me see if we can see this one. Now, okay. Oh. Okay, this is the approach when we have two robots or several robots, and they share the observations, they share their decisions, and they do together a collaborative task, both robots at the same time. Okay. Okay. Finally, there is this human-robot interaction, and that operation is a handover. And in this case, what we are working now, it is predicting the action of one human in doing a handover operation. And with that, what we are doing is using an attention-based deep learning method in order to know what is the motion of the arm of the person. And with that, we compute what is the future motion of the skeleton of the person. And actually, we know, with that, we know where the person is going to do. And with that, we use that in order to plan what is the motion of the robot. It's something similar to what you have seen in the searching, collaborative search, but here the robot look the skeleton and predict the motion of the skeleton of the person. And let's not see again. Sorry. And as I tell, the robot look the skeleton of the person, looks what is the motion of the skeleton, and looks what is the next action of the person, and then with that, we'll able to do the handover operation. There is something that you see here, the first part of it, because it's the prediction of the person. Now we are working in the shared plan between the human and the robot in a way that the robot is able to detect what is going to be the skeleton, what is going to be the end effector of the person, and with that, what is going to be the object to be given or to be picked up by the robot. Okay, that is a complex operation. Then we are now working on it, and we will apply not only for handover operation, but also in a new project that we have that is Canopies, that is a European project, than where robots and humans has to do harvesting, in this case of grapes, and how both do collaborate together in order to do the harvesting of cluster of grapes by helping each other. The robot and the human do together operation, but the robot has to take care of safe issues has not to be so close to the person to hit him, no? And then it has to predict what is going to be the different situations and try to avoid to be too close. But anyway, they have to be close, because finally, in the handover operation, the robot has to give the object, or the person has to give the object to the person. And in the case of the harvesting, the human has to human has to help the robot to pick up in complex cases and the cluster of the grape, or do other operations. That is a typical issue that happens when two persons are doing a collaborative task. No? Okay, that's all by my side. If you have any questions, now I am able to answer.
Alberto, you have a question on the chat by Gloria Beraldo.
Mm-hmm.
I don't know if you have answered it during the presentation. How did you estimate the human position after 5 seconds? Here another by Andreas.
Okay. Okay. What we do is we detect with the LiDAR, that is this laser scan. Then we have 360 degrees, and we are computing every time what is the position of the different persons, and also with that we predict, we track in different milliseconds before, and we predict what is the motion of going to be using this LiDAR. Okay, and then we do, this LiDAR has a length of up to 30 meters, and actually but our horizon, then the motion is 5 meters, and then we can detect whatever is moving around these 5 meters, actually over that, and then we can predict what is going to be in the future using this LiDAR. In very busy, the second is Andrea says, in very busy streets in cities like New York or large groups, how it react? Okay, well, here we have made many experiments with simulated and also with real. But with real, with very crowded situation, we have not simulated, we have not doing this real experiment. We have made simulation with thousands of people, okay? And then what happened, it is there are many, the behavior of the robot, it is different depending how crowded it is. If there are too many people, the robot can have can react in a conservative way, that is trying to stop and go very slowly, or can react in a way to be more forcing the situation, and it try to push a little more. We can change this situation. We can put the robot to be conservative, or could be more proactive, or to be more. And that is something that that we can also detect. We have another work than look for the person, the emotion of the person, and try to interpret what is going to be the behavior of that person. There are some people that wants to be very far away from the robot, and other people wants to be very close. And we can detect a priori which is the kind of person, and try to incorporate that also in our motion of the robot. Okay. What is the architecture of your network overall for human motion prediction in the drone following? Okay, in this case we use in this specific case we use a typically multi-layer perceptron for that one. We use 2 multi-layer perceptron, not complex ones. Fully connected, yes, ones we use. We use in another cases LSTM, okay, recurrent ones, but and also we use other type of GANs, etc. But in this specific case, we use typically multi-layer perceptron. Okay. Yes, Rajesh, we are using the 3D LiDAR for predicting the motion of the person. Yes, also we can incorporate in some cases the stereo vision in order to identify the person, to be able to approach that person. No? Okay, Kirill says in the first example about collaborative exploration, did the person also have some kind of sensors? No, the person has nothing. I mean, the person is the only what it uses, it is the mobile phone. And with this mobile phone is what both the robot and the person share their own knowledge. What is important to understand, it is the robot doesn't know how the person is thinking. However, the person is giving this information through this graphic interface, because the person gives what, in some cases, what is its position, or give what is the future destination, and then and also can tell to the person where the robot has to go, and that is a way to overcome this difficulty to know what is the person is going, what is the intention of the person, or what the person is going to do. And also we use, and that is an important issue, we do that very short time. Could be in few seconds or could be in milliseconds. That depends on the reaction of the person. But anyway, we can use in the future, could be that probably we use sensor in the person. But we try now to avoid that. We try to detect as it is the person, and we try to understand the intentionality through this interface, okay? Okay, good.
I think you have a question by Florian that you have passed through.
Yeah, but is in the chat or is?
Yes, I think so. Florian, if not, you can open your microphone if you want.
Yes, I was a bit of a curious. Just how would the robot behave if you hug him? If you give the robot a hug?
How the robot behave?
Yes, if you give him a hug. So if you un abrazo.
Well, okay. When we use the part of the social force model, the social force model is a reactive, okay, behavior. That means that sometimes the robot, if the forces are too strong and try to push back the robot could go back, okay? Depends of this combination between the attractive and the repulsive forces, and then can be then we do one other. Let's say it can be then the robot go in front, or can be then the robot go back. Also, this combination, as you see, there is a linear combination one way, but also we use this neural net. This neural net computes in a non-linear way the forces that combines, and that means that sometimes that can be then the robot tries to approach, sometimes tries to go back. And also we have in the rear, we have a safety behavior. Then always we try to avoid any collision between the human and the robot. And this is something that always is in the back in case then the robot is approaching too much or the person is approaching too much, okay? Then we can have these two kind of behaviors. Mm-hmm.
Okay, so it will try to escape when you want to hug it.
Escape? No, we don't give this possibility now. We can have this give this information of escape, but we didn't give now at present. Okay, in our behavior we didn't put it. In the future, we are considering in the human robot interaction that could be cases where the robot has to go back and escape. Yes, could be. Or could be that the person doesn't really do the operation of the handover, for example. The person can, instead of do the object, go away. And that how the robot has to react. This is something that we are considering because we are predicting what is the action that the human is going to do. And then, but we are considering that, we are predicting this behavior, but we have not included that. Okay. Okay. I think with that, thank you for attending. And now Juan Andrade is going to present the other talk. Okay. Good. Bye-bye.